Thank you, Kampo, and thank you, Ari, for kind introductions. And today, my talk focuses on the molecular spin qubits for quantum computer and high-density memory devices based on molecular magnets. So everyone knows, last year, Nobel Prize in Physics is given to the experimental evidence of quantum entanglement. So this quantum entanglement is strongly correlated to the spin qubit and also quantum computer. Today my talk is two parts. First, I focus on the quantum computer, and secondly, I focus on the high-density memory devices. So then for the quantum computer, first I focus on the spin qubits and the coherence at room temperature. Everyone knows, every day you use a personal computer. Personal computer is composed of the classical bits, 0 and 1. But quantum bits, qubit is a superposition of 0 and 1. If you use the classical bits, calculation takes 12 days. However, if you use a qubit, quantum bit, calculation takes 60 minutes. Huge progress. So you must realize quantum computers. So then, as I told you, minimum unit for quantum information is a superposition 0 and 1. So for the quantum computer, now first quantum computer is working in IBM. So quantum computer put into the liquid helium, so the low temperature is okay. However, more recently, so qubit available for the quantum sensor to apply biological systems, then room temperature is needed. From this point, room temperature is better. So how to create the best qubit is most important thing. So, rules of the DySc2N. So first one is the scalable with well-characterized qubit, the ability to initialize the state of the qubit to a simple fiduciary state, and non-relevant the coherence times, a universal set of quantum gates, and also a qubit's specific measurement capability. These are very important to realize a good qubit. So then, several qubit candidates for the quantum photons and the quantum dot and the superconducting loops. So IBM uses this superconducting loops for the quantum computer and also trapped atom and nitrogen vacancy in diamond. However, more recently, molecule-based magnets become a next candidate for the qubit because the merit is a spin pulse phase controlled by pulse-PR, high spin polarization of electron spin, high molecular density. However, demerit is a short lifetime of superposition spin-spin relaxation time. We must elongate the T2. So this definition, spin-spin relaxation time T2 and spin-lattice relaxation time T1. Everybody knows. So boundary region is twice T2 is larger than, twice T1 is larger than T2. So in this sense, longer T1, T2 is needed. So as I told you, spin-lattice relaxation T1 is factor to T1 is the inner magnetic field, such as nuclear spin and magnetic dipole interaction. And also, spin-spin relaxation time T2. Factor induced to T2 is a nuclear spin, negative spin, and the rotation measure. So this is a summary of the T2 of molecule-based magnet. So usually T2 more than 100 microseconds is enough for the calculation. And also, room temperature. Oxyvanadium phthalocyanine is almost room temperature. From these results, molecule-based magnet is very good candidate for spin qubit. So then typical one is oxyvanadium spin 1 system, square pyramidal and octahedral. Depending on the compounds, the decay time is different. And also, this is a magnetic property. This is an optical property, terahertz. You can see 2 peak or 1 peak. So depending on the compound, terahertz region, peak is split or not split. So then we must realize the correlation between magnetic properties and optical properties. So this compound 1. So this is 2 relaxation time. So 2 relaxation time. So in this case, in the terahertz, 2 peak. And this compound 2, single relaxation, in this case terahertz region 1p. So we realize relationship between magnetic and optical properties. Terahertz region is very important to detect the lattice. So then, as I told you, typical one is a square pyramidal oxyvanadium spin-1 system, and also octahedral vanadium system, also spin-1 system. So far many investigations for the vanadium 4+ and kappa 1+, kappa 2+. But other candidate, chromium 5+, cobalt 2+ low spin, nickel 3 low spin, iron 3 low spin, all spin 1/2, one spin system. This is not sigmoid magnet. This is just molecule-based magnet. I focus on this all spin 1 system. So, and the outline for spin qubit and coherence, first one is a crystal engineering method, so-called morph spin qubit. So the suppression of intra and the intermolecular vibration of oxyvanadium TbP by using 3D morph. So you know, kappa MT in the crystal, kappa MT is planar structure. However, in the high vacuum condition, distorted structure. This means the crystal lattice will suppress intramolecular vibration. So lattice is very important. Then I focus on the oxyvanadium TbP. So then starting material, zero-dimensional, soft lattice, but put into the metal organic framework more very strong lattice to make clear the factors of spin behavior influenced by the crystal lattice. So then we synthesize tetracarboxyl benzyl TBP, zero-dimensional starting material, to put the zinc to make a two-dimensional material, to put the bipyridine to make a three-dimensional compound. We compare the zero-dimensional and the three-dimensional compound. So this is a crystal structure, zero-dimensional compound, vanadium distance here, and this metal organic framework morph. So metal distance is here. We compare both compounds. So this EPR spectra diluted in the titanium oxide diamagnetic species, three-dimensional and zero-dimensional. This analysis. So D perpendicular, D parallel, same. This means that zero-dimensional, three-dimensional material has the same electronic structure. However, as I told you, in the terahertz spectroscopy, zero-dimensional has a very sharp peak around the 67 wave number. This is deformation of the molecule and the stretch mode of the metal ligand. Yeah, like this is theoretical calculation of molecular deformation. However, in the three-dimensional mode, no peak, because we suppress the lower energy of the deformation of the 3D mode due to the rigid lattice. So then, this is a result. Three-dimensional compound, quantum coherence observed even at room temperature. And also, Rabi nutation. Usually, Rabi nutation observed very low temperature. Rabi nutation, we use a pulse field, we detect the echo. But our compounds, even at room temperature, very beautiful Rabi nutation is observed. So then, in the case of 3D morph complex, Rabi nutation or coherence was observed due to the rigid lattice at room temperature. So from this finding, kappa is another good candidate, but the bulk kappa compound shows an anti-ferromagnetic interaction. Then we dilute it to the one-dimensional, two-dimensional, and three-dimensional non-magnetic materials. So then we isolate kappa to one molecule. Then it should be show the spin quantum molecular spin qubit. So for this purpose, platinum 242 mixed bias compound counter the perforate this molecular ligation. So in this case, one-dimensional lattice, but changing the counter ion to hydrogen, two-dimensional network. This is a one-dimensional lattice. This is a two-dimensional lattice. All platinum 242 mixed bias compounds are diamagnetic species. So in this compound, we dope the kappa 2, 5%. So one-dimensional compound shows a slow magnetic relaxation, and two-dimensional compound shows a slow magnetic relaxation. So then two-dimensional material is longer lifetime compared with the one-dimensional, so stronger lattice. So then finally, we dope kappa into metal organic frame wire. So zinc MOF is a typical diamagnetic species. We doped copper, same structure. Copper is doping. So slow magnetic relaxation of ZAR. This is not sigmoidal magnet, but a phonon bottleneck effect. So we realize slow magnetic relaxation and spin qubit. So from the RS plot, due to the phonon bottleneck effect, not sigmoidal magnet, but the phonon bottleneck effect. So let's put the gTensor engineering method. So relationship between anisotropy of G values and the T1 in oxyvanadium TPP and the chromium nitride TPP. So originally, gTensor engineering is reported by Richard Penny in Manchester, multi-bit system by using anisotropy of G values and the space arrangement. However, we use electron spin will be influenced by the vibration if G values have high anisotropy. So then, oxyvanadium, one spin system, chromium nitride, one spin system, same electron structure. To make clear the influence of anisotropy of G values to T1. So this is the crystal structure. Vanadium or chromium are distorted from the square TPP. So this EPR spectra diluted into the titanium oxide diamagnetic species. Chromium nitride, this oxyvanadium, this G anisotropy. Chromium nitride 0.0398, oxyvanadium 0.0235. Chromium has a larger anisotropy. What's happened? So then this is the result. Chromium nitride shows a faster relaxation time, but the oxyvanadium shows a slow relaxation because chromium nitride larger anisotropy. So both compounds show the slow magnetic relaxation. This is not sigmoidal magnet, but a phonon bottleneck effect. So then oxyvanadium is better than chromium nitride due to the smaller anisotropy of G value. It is so-called gTensor engineering method. So the third method is the orbital engineering method. Relationship between different occupied orbital NIC3 complex. NIC3 complex is very unstable, but we compare the octahedral NIC3 and the square pyramidal NIC3. So for example, macrocycle ligand stabilizer NIC3, axial ligand NO3, counter NO3. This is abbreviated NIC-NO3. Axial ligand chloride and counter perchlorate. This is abbreviated NIC-chloride. So pure nickel chloride shows an antiferromagnetic interaction. However, we dope in the cobalt-3. Cobalt-3 is a diamagnetic species. So the NIC3 is isolated. We can detect the NIC3 and this shows the molecular spin qubit. So this is EPR spectra. So ampere electron is located in this scale orbital. And also both compounds show the slow magnetic relaxation. This is not sigmoidal magnet, but a molecular magnet. And this nickel NO3, this nickel chloride. Nickel chloride faster relaxation time because chloride has a nuclear spin, but the NO3 coordinated by oxygen. Oxygen has no nuclear spin. Then nickel NO3 is longer lifetime. So we switch to the planar nickel 3. So bulk nickel 3 compound shows an antiferromagnetic interaction. Then we dilute it into the diamagnetic gold compound. So then we isolated nickel 3. So in this case, ampere electron is DXC orbital. So then this shows a slow magnetic relaxation. This is not sigmoidal magnet, but phonon bottleneck effect. So these are all data, all compound. Planar nickel 3 shortest because strong molecular deformation, molecular stretching mode. But macrocycle stabilize nickel 3. So then chloride and NO3. So NO3 is longest lifetime and chloride and planar compound. So then from this approach, so we must realize molecular spin qubit at even at room temperature and also longer T1 and T2 longer coherence time. So let's move to the high density memory devices. First one is single molecule memory performance by single molecule magnet. So metal-fluorine single molecule magnet encapsulated into single-walled carbon nanotube with giant magnetoresistance, metallic conducting single molecule magnet with giant magnetoresistance, and the photo-switchable single molecule magnet. Every day you use a classical magnet, but every day I use a single molecule magnet. Why? Why should we use single molecule magnet? instead of classical magnet. Why? To overcome Moore's limitation. Human being faced the Moore's limitation. We must overcome Moore's limitation. Unfortunately, Moore passed away 1 month ago. So everyone knows Moore's law. Every 1.5 years, memory capacity increased twice according to Moore's law. Then now 2 or 3 years. Around here, in order to increase the memory capacity, we must make the classical magnet smaller into nano size. However, classical magnet does not work in the nano size, just quantum fluctuation. So then we must use a nano-sized magnet such as a single-molecule magnet, such as double-decaphthalocyanine terbium single-molecule magnet. That's why we use a single-molecule magnet every time to overcome the Moore's limitation. So everyone knows single-molecule magnet. Classical magnet is a three-dimensional ferro or ferrite magnetic interaction, but the single-molecule magnet is a zero-dimensional. No intermolecular interaction independently exists. However, one single-molecule magnet has a double potential. Below broken temperature, upstream or downstream freeze, and the magnetization, it shows a hysteresis. One molecule works as one magnet and one memory. This is a very good candidate. So then, this is another view. Below broken temperature, upstream or downstream freeze. This is thermal relaxation, observe the hysteresis, and quantum tunneling occurs. So you can see, this is thermal relaxation, hysteresis, and you can see the step. This is a quantum tunneling. This is available for the memory devices and the quantum computer. So frequency dependency in AC susceptibility. In the classical magnet, we see from 1 Hz to 1000 Hz. No frequency dependency in classical magnet, but single-molecule magnet, zero-dimensional. Very beautiful frequency dependency in AC susceptibilities observed. And also heat capacity, very powerful to detect the ordering. So in the classical magnet, antimatter magnet, at the needle point, three-dimensional ordering occurs. Very sharp peaks observed in the heat capacity. However, single-molecule magnet, zero-dimensional, no ordering, no peak, perfectly different classical magnet and single-molecule magnet, so-called 21st century new magnet. So our final target in Japan, National Library has a 20 million books. All information are stored into the sure cubic size memory devices. So another important point is Spintronics. Last century, electronics. This century, Spintronics. Electronics is based on the freedom of charge of the electron, but Spintronics is based on the freedom of charge and spin of the electron. So then Spintronics has much advantage compared to the electronics. So then for the MRAM, advantage of Spintronics is no volatility of information, high operation speed of nanoseconds, high information density, low consuming electric power. This is a big advantage compared to the electronics. So several electronics Spintronics include the magnetoresistance. Typical one is the giant magnetoresistance and tunneling magnetoresistance. Every day you use a GMR, TMR in your personal computer, and CMR, BMR, EMR, all magnetoresistance and Spintronics. So let me show the first example of giant magnetoresistance. 1980, Professor Gurenberg and Feld discovered. They got the Nobel Prize 2007. So this is a classical magnet, non-magnet, classical magnet. Spin is anti-parallel, low conductance. Then definition is 0. Spin is parallel, high conductance. Definition 1. 0, 1, 0, 1 switching in the classical magnet, your personal computer. However, to overcome the Moore's limitation, we must use a single-molecule magnet instead of the classical magnet. Every time we use a single-molecule magnet to overcome the Moore's limitation. So for this purpose, usually we use a scanning tunnel microscopy STM. This is an instrument for imaging surface at the atomic level, and also scanning tunnel spectroscopy STS. This provides information about the density of state. So the DIDV, tunnel conductor DIDV, is directly proportional to the sample dose. We usually use this STM and STS, very low temperature. We operate these STM and STS. So first topic is the single-molecule memory performance by single-molecule magnet. We put the information to the single-molecule magnet, downspin, upspin. 0, 1, 0, 1 into the single-working magnet to overcome the Moore's limitation. For this purpose, we use a tunneling resistance. You can see hard disk spin is parallel, high conductance, then division 1. Spin is antiparallel, low conductance, division 0, 1, 0, 1, 0 switching. But this is a classical magnet. We use a single molecule magnet instead of classical magnet to overcome the Moore's limitation. So then how to write and read one memory in single molecule magnet? So STM chips is electrode 1. Single molecule magnet sample is electrode 2. We use tunneling resistance for realize write and read one memory in the single molecule magnet. So as I told you, we use a tunneling resistance, spin of the chips, SM chips, and the spin of the single molecule magnet parallel, high conductance, division 1. Spin is antiparallel, low conductance, division 0, 1, 0, 1, 0 switching by the tunneling resistance and using the single molecule magnet. So, but you must believe now spin is up or spin is down. So then I must visualize. For example, spin down, dark color, division 0. Spin up, bright color, spin up, division 1. From the color of the spin, dark color, division 0. Bright color, spin up, division 1. So from the color change, we put, you can distinguish now spin down, spin up. So we use this visualization. And the other important point, the chip of the spin polarization, usually platinum iridium tips and cobalt, bulk cobalt is a ferromagnet. We put the platinum iridium to the bulk cobalt to take off one cobalt atom. One cobalt atom is a paramagnet. We usually use the platinum iridium, one cobalt atom. So this is our STM chips. So this is a result by using the classical magnet. Cobalt iron is a classical magnet. You can see bright spot. Bright spot means spin up, spin up, spin up. Dark color, spin down. 1, 1, 1, 0. 1, 0, 0, 0. 1, 0, 0. Like an oscillator, black, white, black, white. So this we show the moving from, we move to the extramagnetic field from minus 1.0 Tesla. So we sweep the extramagnetic field. You can see flip. So spin down, 0, 0. Spin up, 1, 1. We put the information in the classical magnet. Upspin, downspin, 0, 1, 0, 1 into the classical magnet by using the spin polarized STM. It's the first observation of the direct observation of the spin up, spin down, 0, 1, 0, 1. So in this case, spin down, down, spin down, up, spin up, up. So you use the tunneling resistance, end up, up, down, down, down. So large states observed, then timelines observed. So we must realize single molecule memory devices by using a single molecule magnet. This is a double capital shiny single molecule magnet. We access to one molecule. You can see now 2.5 Tesla, now 2.5 Tesla. Dark, this is a single molecule magnet, one molecule. Access to one molecule by STM. Now dark color, spin down, we sweep the external field. So now external field 2.5, 2.0, 1.0 color change. Now bright color, spin up. We put the information into one molecule, down, up. 0, 1, 0, 1. Okay? You can see again. Now 2.5. This is dark. Spins down. 0, 0. This is a single magnet, one molecule. Now color change. Up, down, up, up. So division 1. Now color change. 0. So we realize. Put the information up, down by using a single magnet. So this final application, unfortunately, this is Japanese. You cannot understand because this is top secret for the foreigners. So then I read Japanese PowerPoint. So make a monolayer, we sweep, put the information, we sweep, read the information. So to realize high density memory devices, so let's move the metal fluorine single magnet encapsulated into single carbon nanotube with giant amount of resistance. So you know, single carbon nanotube, 80% metal, 20%, 80% semiconductor, 20% metal. We inserted the single magnet, conduction electron and local single magnet interact to show the negative amount resistance. This is a new Spintronics. So metal fluorine disposition one or double capital sign inserted. So this is a pivot motif. So very easy condition, high temperature, high vacuum condition. So then 2 days sublimation, wash upside. So this is a table image, this is a motif. You can see metal fluorine is inserted. This is EDX, scandium disposition actually included. So encapsulation is success. So the Raman spectra is very powerful to detect the charge transfer between metal fluorine and single carbon nanotube. After encapsulation, rate shift is observed. This means that charge transfer occurs from the metal fluorine to the single carbon nanotube. Single carbon nanotube and the metal fluorine interact, charge transfer occurs. And in this point, the coercivity. Before encapsulation, coercivity is 0.5. After encapsulation, 4 kilo state. So large states, this means to suppress the quantum tunneling at the ground state. So then unfortunately this is Japanese, this is a big top secret for the foreigners. So then by electron beam lithography, we take one carbon nanotube, put the electrode to measure the negative amount of resistance. So then for this purpose, this is a single carbon nanotube, one carbon nanotube, and the electrode is gold. No negative amount of resistance. But we switch from gold to nickel. So very small, but 0.37 negative amount of resistance observed. So this is the first observation of negative amount of resistance. This is due to the conduction electron of the single carbon nanotube and the local single magnet interact. So this is another Coulomb blockade oscillation. This electron beam lithography. We take one carbon nanotube. This is a palladium electrode, this is a palladium electrode. And before, after encapsulation, we compare the Coulomb blockade. Coulomb blockade means the quantum conductance. So before encapsulation, after encapsulation, we compare the Coulomb blockade oscillation. So this is before encapsulation, very beautiful oscillation observed. We switch from the external field, no effect because no spin in the carbon nanotube. But after encapsulation, very noisy Coulomb blockade because interaction by conduction electron and local spin flip. Then red one noisy, and we added 2 Tesla. Red color changed to blue. So magnetic field shifted the Coulomb blockade oscillation. So then let's move the metallic conduction single magnet with giant amount of resistance. So then this is organic, metal organic superconductor and the single magnet here. By electrochemically, we obtain the donor acceptor compound. By d-pi-f-pi interaction, we realize giant amount of resistance. So for this purpose, donor is a good candidate for metal or superconductor BEDO and the single magnet cobalt. We obtain the single crystal by electrochemical method. This is a compound, beta double prime, this kind of stacking of the BEDO. Okay, so this is a crystal structure, this is a BEDO, and this is a single magnet BEDO, 2-dimensional layered bifunctional materials. So then, Raman is very effective for estimate the charge transfer from donor to acceptor. 0.23 charge transfer occurs. So this is a conducting single magnet. So then it shows the hysteresis, actually magnet, single magnet. And also frequency depends, very beautiful. This is evidence of single magnet. And also measure the conductivity. This is a metallic behavior down to 12 Kelvin. This is the first observation, metallic single magnet. With increased magnetic pressure, 1000 Gms, but not superconductivity. Metal initial transition occurs. But this compound shows a negative amount of resistance. Conduction metal and the conduction localized single magnet interact to show the negative magnetoresistance. So then the Fermi band calculation, actually this is a method. Finally, we must realize giant magnetoresistance by using spin bulb method. Cobalt substrate sublimate the one single-walled magnet and chromium chips. So DIDB, 0 Tesla, 5, and 1 Tesla, 10, twice. So finally, by using this system, by using spin bulb method, we realize giant magnetoresistance 200%. So we can overcome the Moor's limitation by using the spin bulb and one single-walled magnet. So then next, how to increase the history temperature. Now highest history temperature of single-walled magnet is 80 Kelvin. Professor Richard Layfield and Liang and Lin Yang Tong reported. However, we must realize room temperature. So then to increase the energy gaps between the ground state and first sublevel, and to suppress the quantum tunneling mechanism QTM in the ground state. Both are very important. So then if the potential barrier very high and realize a high history temperature, but if the quantum tunneling occurs at the ground state, history temperature very low. So we must suppress the quantum tunneling at the ground state. So then for the double after assigning two methods, ideal square anti-prism SAP and also exchange bias for ground state. So then upper after assigning, low after assigning, no distortion, square parallelism, D4H. In this case, ligand phase includes the B44 and the B64. B44 and the B64 is exact source of quantum tunneling. However, upper after assigning, low after distorted 45 degree. D4D, D4H change to D4D. This ligand phase not include the B4 and B64. Then square anti-prism suppress the quantum tunneling. And also exchange bias. This is a diamond model. This diamond shows a, you can say, step at the 0 Tesla, at the ground state, no step. This means no step means no quantum tunneling in the ground state, because two spin at the same time flip two spin. This two spin flip possibility is very low. Then we can use a two spin system to suppress the quantum tunneling. So for this purpose, my student synthesized double capital assigning bridged by benzene to make a two spin system. So his temperature increased 25 Kelvin, starting material 4 Kelvin. But by using the exchange bias, his temperature 25 Kelvin. And another fuse type double capital assigning, his temperature 27 Kelvin. And finally, my student synthesized liquid crystal stacking. So then 31 Kelvin. But we must realize room temperature, hysteresis, to real application. So then today I talk about the quantum computer for high density memory devices, and for the quantum computer spin qubits and coherence even at room temperature, high density memory devices, single-walled memory performance by single magnet, metafluorescent single-walled magnet encapsulated into single carbon nanotube with giant magnetoresistance, and metallic conducting single-walled magnet with GMR. We skip the photo switchable single-walled magnet. But finally, I must stress, what is science? What is science? Everybody knows, but everybody does not know, unfortunately. So of course, to create new concept, of course, to create new concept, new compounds, new physical properties, new reactions, new theories, new measurements. But everybody does every day. This is the science. Most important thing for science is to create new research field. It takes 30, 40 years. You must create new research field. So my field is a multifunctional nanoscience or advanced metal complex. Multifunction between magnetism, optics, conductivity, magnetism. But many researchers work on the multifunctionality. But I focus on the metal complex and also nanoscience. Nanoscience means today I taught quantum effect and non-linearity. Today I didn't show the non-linearity, but today I focus on quantum effect. So this is my field. It took 40 years to realize this research field. So science should be not number one, but only one. If number one is overcomes other researchers, Number 1 become number 2, number 3, number 4, number 10. Nobody remember number 10. But only one. If you forget, you can check the textbook. You can find out the only one. Then science should be only one, not number 1. And also science should be not from 1 to 100, but from nothing to 1. From 1 to 100, these are just development of other researchers' work, not no originality. Most important thing is from nothing to 1. This is actual pioneer and create a new research field. So science should be from nothing to 1. So then natural science, 100%, already clear fields only 5 to 10%. Other 90%, more than 90% unclear. But unfortunately, most researchers work on already clear field. Unfortunately, very boring. You must challenge to the unclear field. But it takes 40, 50 years for your only one life, only one chance. But most researchers failed, unfortunately. So then, what is science? As I told you, to create a new research field, it takes 30, 40 years. So only one chance for your only one life. For the student, you have a chance. But other all researchers, no chance. Unfortunately, I don't know. But some are very old. I'm still young. I have another 50 years for my life. I challenge the next project. Okay? So generally in Japan, Japanese people pass away around average 90 years old, very old. Like Turkey, 90 years old. But you sleep every day around 80 hours. 8 hours means that one day is 24 hours and 80 hours. 8 hours means that 1/3 you are every day sleeping. In that sense, for the 90 years, you sleep for about 30 years you are sleeping. Too much. Only 3 years, not 30 years. Only 3 years enough. So once a week you can sleep. That's enough. You lose the time. In my case, when I was a Masahiro student, every 2 days, just I sleep 2 or 3 hours. Every 2 days. Don't sleep. Don't eat. No holiday. For me, more than 30 years, no holiday. Every day I attend my lab and my office. So, and finally, I acquired my many co-workers. So, international collaboration and theoretical handlement and devices. And also, 3 years ago, I retired. But I keep my lab. And this around 10 years ago, biggest lab, more than 55 members. And many international, China, India, Egypt, Bangladesh, China, France, many international. But unfortunately, I don't remember the name of my students, unfortunately. Thank you for kind attention. Thank you.
Is any question for this top secret talk? Yes, there.
Hi, thank you for the nice talk. I have a question about your quantum part. Quantum part of your presentation. Quantum computer part. You demonstrated 2D structures of molecular layers. Do you have an intention to repeat, for example, D-wave annealing experiment or Google superiority experiment in the near future?
Yeah. Good question. So, in the molecular spin qubits, in the superconducting loops, they make a circuit. But in the molecular spin qubit, we must use EPR STM. We access to one molecule to detect the spin. Okay? This year I published in Nature Nano, nano letter in this year. We success to detect one spin system. So then from this point, not 3 dimensions good, 2 dimensions is enough. Because 2 dimensions is very easy to access. 3 dimensions in the depth, very difficult, on the surface. So then 2-dimensional material is better, I think.
But are you able to manipulate several? How you can prepare initial state for multiple?
Yeah. It's a good question. As I told you in the DySc2N rule, so we can easily initialize by perseverance. We usually use the perseverance and we set up the spin. So then very easy. Yeah. A bit initialize the state of the qubit. Yeah. By using the perseverance.
With respect to quantum computing devices, the integration is essential and the quality of interfaces. So you showed some encapsulation in single-walled nanotubes. Is this one of the best ways to proceed for that, or do you have another secret that you do not want to say?
I'm sorry. So, yeah, you have a good suggestion. So, carbon nanotubes is very good for real devices because we can arrange one-dimensional or metal-metal molecular interaction, or we can manipulate easily by using the single carbon nanotube. But sometimes very difficult to obtain the electron beam lithography, only one carbon nanotube and put the electron. That's a very hard work to make a device. But the carbon nanotube is very promising.
Other questions? I have a question for you. Here.
Yeah.
Then you were discussing about the high-density memory devices.
Yes.
And you want to go over the Morse law. But there are another important parameter, which is the access speed. How do you access? How many do you invest to access the information? How your proposition compares with the solid state devices that we have today?
Good question. So this typical example, this is one single magnet by using a spin porous STM and access to this molecule and puts the external magnetic field. And after that, move to another molecule. So it takes time. So then, as I told you, this is top secret in Japanese, okay? This monolayer, all molecules are one-dimensional alignment. So, and we use a multi-spin system. So we ship.
Yes, it's a kind of...
many chips. And at the same time, put the information and read the information.
How many microseconds or
But you know, one molecule works as one magnet, one memory. Very slow time, but much high density. Okay? Different from the classical magnet. So then, this is a very promising method.
Other questions? Yes.
And how long can you keep your memory in particular state? What's the destruction time?
Yeah. And for example, this case. So you can see from 2.5 this spin down, and we sweep from 2.5 to -3. So in this case, this division 0, and in this case division 1. We put the information 0 to 1, but depending on the scanning ratio, so time is determined. If we do the slow sweeping, the magnetic field, so and memory time is longer. Another important point is that this single magnet, system temperature is less than 4 Kelvin. So then we did this experiment below 1 Kelvin, very low temperature.
Yeah. If you set this memory setting state to 1, what's the lifetime of this state?
Yeah, of course. Usually in the classical magnet, we must keep the 5 years for using the classical magnet to the memory, 5 years. But in this case, 5 seconds. Too fast.
And did you try to measure several cells simultaneously in proximity?
Yeah.
You tried?
Yeah.
So several cells and they all of them?
Yeah. And this last national project, and we collaborate with the Sony company. But the Sony company shift from the magnetic memory to the optical memories. So then our collaboration stopped from Sony big company. So then we must contact with the other company.
Okay, thank you very much. Now we have a break for 15 minutes and then we will continue.